General relativity is a theory of gravitation that was developed by Albert Einstein between 1907 and 1915. According to general relativity, the observed gravitational effect between masses results from their warping of spacetime. In the presence of mass and energy, the geometry of spacetime is altered, creating a curvature. This curvature influences the motion of objects, which we perceive as gravity. This is different from the Newtonian view of gravity, where gravity is seen as a force between two masses. The following are considered today as the experimental evidences of general relativity. Gravitational lensing, the bending of light around massive objects, a phenomenon known as gravitational lensing. This was first observed during a solar eclipse in 1919 by Sir Arthur Eddington. The stars near the sun appeared slightly out of position because their light was curved by the sun's gravity on its way to Earth. Gravitational time dilation. Time dilates in a gravitational field, meaning that clocks run slower as they approach the mass that is producing the field. Gravitational redshift. Time dilation causes light to vibrate at a lower frequency within a gravitational field. Thus, the light is shifted toward a longer wavelength, that is, toward the red. This phenomenon is known as gravitational redshift. Precession of the perihelion of Mercury's orbit. The orbit of Mercury rotates over time, a phenomenon known as precession. Detection of gravitational waves by LIGO. Laser Interferometer Gravitational Wave Observatory. Gravitational waves are currently believed to be ripples in spacetime caused by the acceleration of massive objects, predicted by Einstein's theory. However, based on my studies, these observations do not confirm general relativity. In fact, there are better alternative explanations for these phenomena. New studies suggest that mass defects in nuclear reactions or other events in the universe, such as active stars, supernovae, neutron star collisions, black hole mergers, etc., create mass defects on a large scale, and these missing masses explode and become a super thin form of matter that fills the entire universe. This space-filling matter helps to explain all the phenomena discussed before. As a form of matter, it is attracted by massive objects and creates a dense region surrounding these bodies. Light will slow down and refract when it approaches a massive body. This explains starlight bending and gravitational lensing. In a dense region, the vibration of particles such as electrons is restricted by the space-filling matter. Since the density of this matter is higher near massive bodies, electrons vibrate slower and, as a result, they emit photons of longer wavelengths, which explains gravitational time dilation and gravitational redshift. Since the Sun maintains a denser region around it and the planet Pluto is sufficiently close to the Sun, when the planet approaches the perihelion region, the frictional and dragging effect of the space-filling matter results in precession. This explains the precession of the perihelion of Mercury's orbit. Large-scale explosions caused by neutron star collisions or black hole mergers create disturbances in the space-filling matter, which can travel through billions of light-years through space. These types of disturbances can be detected with the help of interferometers. Perhaps the LIGO-Virgo collaborations have detected such disturbances in space. So in conclusion, Newton's idea that gravity is an attractive force still remains valid.